So here's what we're going to do. We're going to say we have a Hamiltonian, and the Hamiltonian is going to contain the kinetic energy for each particle and the potential energy for each particle. We're going to assume that nuclei are clamped, so we don't worry about them moving. It's really the possibility, it's the charge distribution of the electrons we're looking at. But that's the And we will assume, you can't prove it, you can prove it in several one-dimensional model systems, but in general, you can't prove the following. But we're going to assume that there are a set of eigenfunctions of the Hamiltonian that is solutions to the time-independent Schrodinger equation. And we're going to say that the psi I, which we will say start at 0, I starts at 0, on up to infinity, are complete. Now, what do I mean by that? I mean that functions that behave in a similar fashion, that have the same boundary conditions about continuity, about behavior at large distances, any function that behaves similarly can be written as a linear combination of the eigenfunctions of the Hamiltonian. So, for example, I'm going to now pluck some wave function that I'll call phi guess out of the air. And I'm going to claim that I can write that as exactly as a sum with fixed linear coefficients of the eigenfunctions of the Hamiltonian. So it says these two things are equivalent. If they were not, then the psi I would not be complete. But in model systems, we can do it for. We can prove the completeness of the eigenfunction of the Hamiltonian, and we've had no indications yet that it is not the case. So we'll stick with that. Okay. So what we want to show is the following. We want to show that if I take phi guess and complex conjugate it and put the Hamiltonian in there, phi guess, and integrate over all space. And in my language, d tau is the generic integrator of all particles, integrator of all space, is greater than or equal to E naught, where E naught is the exact ground state energy. Okay. Now we just need a couple more things. We need to know that the wave functions for the eigenfunctions of the Schrodinger equation are orthonormal. And so the way I'm going to write that is psi I complex conjugate psi j d tau equals 0 if I is not equal to j, and equals 1 if I equals j. Okay, another way to write that is the so-called Kronecker delta, delta ij, and it just means phi and j are different, that number's 0. Okay, so let's do the following. Let's now evaluate this term right here. I want to take phi guess, h phi guess. Sorry for the handwriting. Okay, well, if we believe that the eigenfunctions of the Hamiltonian are complete, I can write this in the following way. I can write it as a sum over I, sum over j, integral. Yeah, actually, I'm going to put it outside. I know. Ci complex conjugate Cj Now the integral of psi I complex conjugate h psi j d tau. Here you see what I did. I took phi guess written as a sum in terms of I, and I plugged it in there, and then I pulled out the constant, the linear coefficient, and then I put a similar sum in for phi guess on the other side, right here. But I put in a different index here because in principle, you could have all sorts of products. Okay, so there we go. Now, here's a trick. H on psi j, well, I've chosen a specific set of complete functions. They're eigenfunctions in the Hamiltonian. So I could write this as Ej psi j. So now I get a double sum that looks like this. Ci complex conjugate Cj Ej psi I complex conjugate psi j d tau. And then, you know, we went through the work to show above that the eigenfunctions of the Hamiltonian are orthonormal. So this is just a Kronecker delta. So this thing is sum over I, sum over j, Ci complex conjugate Cj Ej delta Ij. And now just think about doing that sum over j. So j can go from 0 to infinity. Ej goes from 0 to infinity, but the only time the whole sum, the term that you get is non-zero is when I and j are equal. This thing really reduces to a sum like this, a sum over I, Ci absolute value squared Ei. That's what it is. Okay. I'd like to turn to you and say so far so good, but you're not there. So I'm going to assume you're okay, and you can ask me questions if you want. So what we have now is the following. We have that phi guess complex conjugate H phi guess is equal to this sum over expansion coefficients times EI. Okay. Now, what I'd really like to show is that this is greater than or equal to the ground state energy. So let me rewrite the ground state energy in a weird way. I'm going to write it as E naught times phi guess complex conjugated phi guess. Because we said the trial wave function was normalized, so this is just 1. But now I'm going to write 1 in a weird sort of way. I'm going to do the same trick I did on this integral right here, using the Kronecker delta and the sum. You just won't have the energy term in it. And I'm going to get something that looks like this. It's going to be E naught times sum over I, absolute value of Ci squared. That's just normalization. Okay. So if this is true, then I should be able to write, I should be able to bring this new expression for E0, this really is E0, I should be able to bring it over to this side and get the following expression. I should get sum over absolute value of Ci squared Ei minus E naught is greater than or equal to 0. So that's a question mark, but if that is true, then this is true. And if that's true, bingo, this is true. We will have proved the variational principle. Okay, so let's just take a look at this. So we've assumed that there are a set of energies associated with the Hamiltonian. E naught is the lowest. U1 is next, and pretty cleverly I've numbered them so they increase in energy like that. So let's look at the terms in our sum. I'm going to do Ci squared, absolute value. And I'm going to do EI minus E naught. So if I is, and we'll do I as well, 0, 1, 2, 3, and so on. If I is 0, then EI minus E naught is 0. And all we know about this is it's greater than or equal to 0, because it's an absolute value squared. If EI minus E naught, if I is 1, then this is greater than 0. This is greater than or equal to 0. And then if EI equals 2, this is greater than 0, greater than 0, and so on. So what do you see? Well, the Ci squareds have to add up to 1. We already know that. And so this is essentially a probability times an energy difference. And what you see is that if in our sum over I, if there are contributions from, I'll even switch colors because it's so auspicious, I not equal to 0, then our sum right here is greater than 0. But if only I equals 0 contributes, then our sum equals 0. What does that say? It says that if phi guess equals psi 0, you get from phi guess h phi guess d tau, you get it exactly equal to 0. If on the other hand phi guess is not exactly equal to psi 0, this integral is greater, excuse me, not equal to, but greater than E naught. And you can see that because if it's the case that your guessed wave function has any contribution from E1 or E2 or E3, you're going to get a positive quantity times a positive quantity, a positive quantity times a positive quantity. You're going to get an expression here that's greater than 0, which means that your total energy for the guessed wave function is greater than E naught. So there you go. All right, if you suffered through that, you're an impressive person.